All right, what does it mean to reset versus to not reset? This is to not reset. If we don't reset this, then we know what are the equilibrium concentrations of hydronium and hydroxide at 25 degrees C. This is pure water. Do you know, what are the equilibrium concentrations of hydronium and hydroxide for pure water? So it was 1.0 times 10 to the minus 7 molar. 1.0 times 10 to the minus 7 molar. That's what it is. But normally when we have an ice table like this, we just reset everything, and so we just reset it to 0 and 0. That is, we're going to just pretend no water molecules have even collided. But that's not true. If I have a beaker of water, the water molecules are colliding as we speak, right? And so I'm just imagining all the water molecules are sitting as is and nothing's collided, nothing's reacted. And so we reset all the hydronium and hydroxide back over to the left. And then we solve this equilibrium problem by saying, now that I've reset all the atoms to the left, I'm going to allow it to equilibrate. So I'll get plus X and plus X molar. And so it turns out we reset all the time. We reset all the time because, oftentimes we don't know what the equilibrium is. So for example, if I'm given something like 1.0 times 10 to the minus 8 molar HCl, I'm going to just leave those all as HCl molecules. In reality, I know they aren't all HCl molecules, but we'll just leave it as HCl molecules and allow them to react with water to form hydronium and chloride. And in this case, initially, I'm going to say I'm going to have all these as molecules and none of them dissociated. That's called resetting. And so we start off with 1.0 times 10 to the minus 8 molar HCl. And then I'm going to say, now after I reset this, I'm going to allow them to collide with water to form my hydronium and chloride. And so at first, all this has been reset to just HCl molecules, and now I'll just let it, but we know what X is because it's a strong acid. And then just allow it to do its thing. So we reset. Every single problem in chapter 16 is reset. Every single one. Okay? Because it's the way we start the problem. Automatically we start it as reset. And so to say that there's no reset, no, there's reset. Lots of it. Starting in 16, every single problem. In chapter 15, though, we reset it when we get stuck. If you're able to solve it without resetting, perfectly fine, no problem. The problem is you don't know if I'm going to give you a problem that requires resetting or not. So you should be prepared. It's like in Chem 4, they'd never give you this. Actually, they would never give you this one. This would be, in Chem 4, they'd never give you that problem because you can get the wrong answer. So we'd never give this to you, right? Unfortunately, in Chem 1B, you have to be prepared for everything. And so we do little tricks like simplifying assumption and reset to help bail us out when we get stuck. A lot of people ask, when do you need to use it? You don't. The problem will tell you. The problem will tell you because you get stuck and either going to leave the rest of the question blank, or you're going to start trying something. So start trying something. I get lots of blank pages, though, unfortunately, because people get stuck. Okay, if there are no questions about 15, then I'll just continue with 16. Are there any other questions for 15? No. 15, only 16 is simultaneous. 15 is only single equilibria. And so you'll never have to solve anything simultaneously in 15. Although, no, shoot, that's wrong. There was a multiple equilibria in 15. I don't know if I signed up for the homework. No. I don't think I did. Okay. So 15, no simultaneous. 16, do you have to solve anything simultaneously? No. To get full credit, all you have to do is recognize that you must solve it simultaneously. But you don't actually have to solve it because it's tough. And so this would be like a bonus point situation. If I gave you a simultaneous equilibria problem, a problem that you can only solve simultaneously, then if you actually solve for the x, then you'll get bonus points. If you just say this, set it up and this has to be solved simultaneously, then you get full credit. And so let's take a look at why that is. And so the example we were looking at was 1.0 times 10 to the minus 5 molar HCN. And then we determined that this had to be solved simultaneously, right? And why was that? Oh, no, that was for the HCl problem. This one would be the one right after that. Because we factored in the water in this one. Even though we factored in the water, it was still the wrong answer. Why was it the wrong answer? How did we determine that this could not be solved stepwise? The HCl problem, 1.0 times 10 to the minus 8 molar HCl could be solved stepwise. That is, we just do it step 1, the HCl, step 2, the water. The HCN problem, we tried to do it stepwise. Step 1, the HCN, step 2, the water, but that didn't work. The reason it didn't work was because it upset the equilibrium, right? What happened was the second step upset the equilibrium in the first step. And so if we were to go back and fix that, then we run into an endless loop. We could never fix one without upsetting the other. And therefore, if you can't fix one without upsetting the other, you have to fix both of them at the same time, which is simultaneous. And so we have to solve this simultaneously. Now how do we solve this simultaneously? Well, we have two equilibria that we solve. If I have 1.0 times 10 to the minus 5 molar HCN, I know HCN is a weak acid. I know it's partially ionized, right? Do you know how much? No, we don't know how much. And so this is why we reset it. Even though there's a little bit of hydronium and a little bit of cyanide there, I don't care about those. I'm going to reset it to 0 because I don't want to deal with it. I just want to approach equilibrium from here. And so this is what I mean by we reset every single problem in chapter 16. We reset it to make it easier for us. Or we reset it because we don't even know what the number is. Do you know what the number is here? I don't, but it's x and x. X and x, well, we'll just say minus x, and then bring it all back here. I didn't lose any atoms. I still have all the atoms there, but now it's reset. Okay, so in chapter 16, we reset it, but Petrucci doesn't call it resetting. He just, this is how you solve it. It's how we solve chapter 16 problems. And I think that one of the problems I have is that I call it resetting, and Raheem might not know because that's just my word for it. Petrucci, it's not Petrucci's word, so Raheem might not be familiar with my jargon for this, But obviously, he's got to be familiar with resetting because we do it all the time. Okay? But we don't, why not call it that? And so here, this is going to be minus x molar, plus x molar, plus x molar, right? And so at equilibrium, we're going to have 1.0 times 10 to the minus 5 minus x molar, and x molar. This is normally what we do. And then we go over here and we look at water, H2O liquid plus H2O liquid. And the same thing with water. I know what it is. For water, I know it should be 10 to the minus 7 molar and 10 to the minus 7 molar because pH 7, right? That's what water is. But you know what? I don't want to do that because having the other hydronium in there is going to upset the equilibrium. It's called Le Chatelier shift. Rather than doing Le Chatelier shift, we do a reset. Reset's much easier. The reset in this case is called the common ion effect, but we aren't going to worry about it. So we reset this to 0 and 0 molar, and then let it equilibrate, plus x molar, plus x molar. And so that means that all the hydronium and hydroxide that are present now shift back to water molecules. And now I let the water molecules collide and then re-equilibrate, so I get x molar and x molar. And so then I look at the hydronium total. The hydronium total is going to be x plus y, right? But I have a major problem here. Do you know what my major problem is? My major problem is this. If the new total hydronium is x plus y, and both of these are in the same beaker, then this is no longer going to be x, this is going to be x plus y. If this is x plus y, then is it still going to be at equilibrium? No. And this was at, this is, shoot. I need to make this y, otherwise I get too many x's. Sorry. Well, we'll have that as y. So over here, this is y at equilibrium. It's no longer going to be at equilibrium. Both of these are going to be perturbed. And so how can I solve this simultaneously? The way I solve this simultaneously is I reset one and assume the other is already at equilibrium. And so the way I do that is this. It's going to look funny. And I need, shoot. Screwed this up. I was going to use the same as the book did. Let me use the same as the book did. So I'm sorry, I'm going to change this one more time. We're going to call this one y, because the book calls it y. It really doesn't matter, but I just want to be consistent with the book. And we're going to call this one x. Sorry. It's the opposite of the way I would think of for naming these, but it doesn't matter because it's solved for both anyway. So basically this setup won't work. We have to change it. we have to change it because both of the equilibria are going to be perturbed by the total hydronium that's generated. And so the way we're going to change this is this. Now, it doesn't matter because we can approach equilibrium from anywhere. So what we're going to do is we're going to do the common ion effect, or we're going to pretend. We're going to pretend that the HCN hasn't done its thing yet, right? No HCN has ionized yet, or hydrolyzed. But we're going to assume that moreover here, the water already has. And so rather than using 0 here, we're going to put in X molar, saying that, oh, water's already generated its hydronium, it's already equilibrated, and therefore we have X molar hydronium already present from water autoionization or hydrolysis. And so that means that at equilibrium now we're going to have X plus Y molar hydronium. Can I repeat that? Okay. So this is how we're going to solve this. Okay, we're going to assume that the HCN has not yet collided. So the hydronium produced from the HCN is 0, and the cyanide produced from HCN is 0. So the HCNs haven't collided yet. We reset everything to the left. But we're going to assume the waters already have collided and produced their hydronium. And so the waters already collided and produced their hydronium, then we're going to have some initial hydronium present from the water here. And that initial hydronium present from the water is like having a lion present, you know? And the Y's, let's say the Y's are like, the cyanide's like antelope, you know, or what do lions like to eat? Antelope. Okay, let's say the Y's are like the antelope. So if we have a whole bunch of like predator present, Y can't grow as big, the population. If this were 0 and 0, then Y can grow bigger because there's no predator present here. But now there's predator present, and so it's going to limit how much HCN actually hydrolyzes. We can't have as much HCN hydrolyzed with what we call common ion. This is called the common ion effect. Common ion effect is like a predator. Does that make sense? And where does the common ion come from? The common ion, this hydronium comes from water. And so we're going to imagine that water's already done its thing and generated the hydronium, right? Mm-hmm. And that's what we're going to generate.
So, I have a question.
Uh-huh.
So because we have hydronium from the water, it's going to shift it even more quickly?
No, it can't shift it to the left because this is 0. So we can't go sub-0.
Oh, that's right.
You're right. If we already have hydronium here, it should shift. You know, the more hydronium we add, it should shift it to the left, but it's impossible to shift to the left. And so it's got to shift to the right, but it's not going to shift as much. This is what we call Le Chatelier's kind of inhibition of the forward reaction. That's what the common ion is going to do. We aren't going to get as much forward reaction. But anyway, that's a side point. The main point here is that we're going to assume that no HCN has reacted yet, but water has, and water has already provided some hydronium. And the hydronium is going to dictate how much additional hydronium I'm going to get from HCN, which isn't going to be as much. The way there are other ways you can visualize this. You know, without common ion, then Ka is equal to y squared. With common ion, then Ka is equal to x plus y times y. Therefore, y can't be as big. Y has got to be smaller because now we have, you know, this x plus y term here. And so this is what we have. So this is what I mean by this, you know, predatory effect for this x here. So does that make sense from HCN's perspective, right? And so for HCN, nothing's happened except water has already happened. Water is going to contribute this amount of hydronium, and then therefore we're going to generate a little bit more hydronium to get a total hydronium of x plus y. All right, now we're going to shift over here to water. And when we go over here to water, what we're going to say is water has not done its thing yet. Water has not hydrolyzed yet. And so the amount of hydronium and hydroxide we have from water is 0 and 0. But what we're going to say is that HCn's already done its thing. If HCn's already done its thing, then it's going to generate how much? We're going to have Y, actually. HCn, we're going to generate Y. And so HCn is going to generate Y, so what we're going to say is we're going to have Y molar hydronium present already from the HCn, and then the water hasn't yet collided, and then having this hydronium present from HCn is going to impact how much hydroxide we can generate. Are we going to be able to generate as much hydroxide? No, because we got this hydronium ready to attack it. And so this is not going to be 10 to the minus 7 molar. The book says it's 10 to the minus 7 molar, but it's impossible. It cannot be 10 to the minus 7 molar because of the common ion effect here. And so this is where the book made the mistake in the solutions manual. It's just the solutions manual that's wrong. The text is right, and the solutions manual, a whole bunch of people contributed to that. So one person just made a mistake. And so then at equilibrium, how much are we going to have? We're going to have Y plus X molar. And therefore this works because do you see the hydronium concentration for both equilibria are going to be the same, and then we can have equilibrium maintained simultaneously in these two equations. And so, well then all we have to do is solve for Y and X. And so if we have two unknowns, we just need two equations, right? Two unknowns, two equations. You've done lots of these in algebra, I'm sure, right? Two equation, two unknown problems. And so let's set up the two equation, two unknown problem. And so the first equation, we'll do the HCN. You know, Ka for HCN was, what was it, 6.3 times 10 to the minus 10? 6.2 times 10 to the minus 10?
Yeah, 6.227.
Okay, 6.2 times 10 to the negative 10, which is equal to the hydronium ion concentration times the cyanide concentration divided by the HCN concentration. And so the hydronium ion concentration at equilibrium is going to be X plus Y. So we'll plug that in, X plus Y. And then the cyanide concentration is Y. And then the HCN, you know, the unhydrolyzed molecules, the unreacted molecules is going to be 1.0 times 10 to the minus 5 minus Y. Okay, the other equation is going to be from Kw here. That's for water. And so Kw at 25 degrees C is 1.0 times 10 to the minus 14. Kw, in fact, all Ks change with temperature. And so usually we specify the temperature. If the temperature is not specified, do you know what temperature you should assume? 25 degrees C. And so this will be at 25 degrees C, which is going to equal the hydronium concentration times the hydroxide ion concentration. The hydronium concentration is Y plus X. I'm just going to reverse it to X plus Y. Keep it the same as that. And then the hydroxide ion concentration is going to be X. And so we have two equations, two unknowns. Okay, and you know, you've done lots of these, right? Two equations, two unknowns, and they don't take that much time, do they? So try this one. Why don't you try to solve this one and see what happens?